all combinations, and higher order Lie brackets like Gj maybe up to k minus 1. The span of this guy is Rn, right? And obviously these guys are subset from B, M, and K, right? Okay. So we will define the concept, which is a very important concept, of extended system. So I'm going to extend my, so this guy is B1, Bm, Bm plus 1 up to Bs. I will call these guys B1 up to Bm, Bm plus 1 up to Br. Obviously R is greater than N, right? Greater than or equal. So I have, like, say, strictly speaking, let's say R is N. I have, like, I span Rn by N independent vectors. Some of them are my vector fields and some are Lie brackets, maybe higher order Lie brackets, okay? So R is greater than or equal to N. The B whole basis may be even more. I'm not using all of them, that's fine, because the B whole basis has nothing to do with this guy. This guy indeed has to be at x naught, right? So the B whole bases are all independent Lie brackets. Then when we evaluate them, some of them may still be independent, some of them may vanish. So these guys are smaller set, but that's fine. Okay, the extended system now is x extended summation j equals 1 up to r bj of x extended vj. So I'm taking these guys, put them here with some inputs as if, so because r is greater than or equal to n, I have here more inputs. This is a fictitious system. So like I said, bj is the same as gj if j is 1 to m. The first m vector fields are the same as my vector fields, but then bm plus 1 up to br are Lie brackets, right? So in this new system, which is a fictitious system, the uj is the same as vj, j is 1 to m. The first m of these are actual inputs, but vm plus 1 up to vr, these are virtual inputs. Okay? So in this system, extended system, I have more inputs. So obviously the steering problem is much easier. I can do it like this because I have, it's as if I have direct control authority over all direction, every direction. So I can do inversion. So I can do the following. I can construct any curve you like. Of course, it has to be differentiable. Construct a gamma of t, or say xe of t star. Okay, some that connects any curve you like. So xe of 0 should be p, and the xe of your final time that you like should be your q. So we wanna here steer. We wanna steer this system. So the objective is to steer here this system from p to q in some time t. Okay? I can do that very easy in the extended system. I can construct a curve, any curve that connects these 2 points, and I can actually generate that curve because I can do the following. So this guy is x1 of t up to xn of t extended. This is equal to, here is the b1 of x extended of t up to br of x extended of t, right, times the v's, v1 up to vr. and I can solve this system. So if R equals N, this matrix is square, I can invert it. Why I can invert it? Why are you sure that we can invert it? So if R is equal, so it is greater than or equal, in particular if it's equal, the least thing, I can actually invert it. So if we call this matrix as B, so V of t is V inverse times X star dot. Right? Why we are sure that we can invert this guy? Or we can solve this system?
Because their span is Rn.
Exactly, because they're satisfying the log, and by definition, B1 up to BR, they are spanning Rn. So I'm sure that they are linearly independent, okay? At least in independent algebra. Very good. So the steering problem is super easy here because we assume direct control authority over the Lie brackets. We assume that they have input associated with each Lie brackets, right? Which is not the case. So the question now is, what is U that does the same job, right? Correct? And to solve this problem, they recalled the theory of non-commutative polynomials. So we will postpone our question here for a while. We're going to go and introduce this theory with this question on the back of our mind. We're going to see how this theory will help us, okay? And how it relates to our world, okay? So theory of non-commutative polynomials. Sometimes, it's also related to the theory of free Lie algebra. But if you have any question, please stop me, okay? Anything obvious so far? Okay, so this is not hard, it just needs a little thinking. It's not hard at all, by the way, it just needs a good way of presentation, which is this is the hard part of it. It's how to present it in a good way. So let's call. So we have a set of polynomials a x1 up to xm. These are the variables like x, y, z. Okay, these are the variables of the polynomial. So a, the set of polynomials in the variables x1 up to xm, but they are non-commutative. Set of non-commutative polynomials in these variables. What do you mean non-commutative? I mean x times y is not the same as y times x. So the polynomials that we deal with every day, they are commutative. These guys are non-commutative. Okay, that's fine. So you're defining from the beginning that x1 times x2 is not the same as x2 times x1. Okay. We define, like matrices, right? Matrices obeys this rule, right? So it depends on how you define your multiplication, really, whether it's going to be commutative or not. Here we're focusing on non-commutative polynomials. And you guys, as you know, polynomials is a vector space, right? Because I can add two polynomials and the addition is commutative. And I can multiply by scalars, that's fine. So this guy is a vector space. And because here they are non-commutative, actually this is tempting to define a Lie bracket. Why? Because I can simply define my Lie bracket between two polynomials x and y as xy minus y times x. You just said that they are not the same. So I'm defining my Lie bracket to be like this, and it's very easy to check that this satisfies the Lie bracket properties, which is linearity. It's linear, you have a scalar, you can get it out. Skew symmetry, you can swap things and get a negative sign. And the Jacobi identity. You can check it very easily. So this is a Lie bracket, okay? So a vector space with a Lie bracket is what? Vector space with a Lie bracket is what? Anybody remembers? It's a Lie algebra, just said. So we have a Lie algebra now, because it's a vector space and it's a Lie bracket. So we're going to denote it by L of x1 up to xm. So these are my polynomials. They are non-commutative polynomials in m variables. Nothing more. It's nothing fancy at all. Here we're focusing on polynomials, but in fact, everything will be valid for whatever you like. Just define your x's and how you like to do multiplication, everything falls out. Actually, they call this Lie algebra in the indeterminates, x1 up to xn. Indeterminates, like I said, it's something to be determined later. We don't worry about them. Okay? They may be vector fields, they may be matrices, they may be polynomials. But for us here, let's focus on polynomials. So this Lie algebra, we can also introduce nilpotency, because we are focusing on nilpotent system. So now it's Lk, x1 up to xm. So any monomial, any term in your polynomial of degree k plus 1 vanish, right? So if you have x1